So welcome to the seminar of the Sony Astani Department of Civil and Environmental Engineering. Today the speaker is Dr. Greg Taylor. Let me tell you a bit about Greg. Greg got his doctorate from the University of Illinois at Urbana-Champaign. He has over 30 years of experience in catastrophic risk analysis with an emphasis on infrastructure systems, finance, policies, and earthquakes. He is presently the Director of Research for Baseline Management Company and is also one of our research professors in the department. Actually, he's teaching a class. If you have not taken the class, I can give you a pitch for the class. It's called C554. It's about risk and decision analysis for infrastructure systems. And actually, I was asking Craig to add, to make sure he covers a bit of asset management, so it tells you about the values and how we can actually use risk decisions to maintain values in our systems. He has over 200 publications in conferences and so on, including 60 journal papers. He has contributed to monographs for the American Society of Civil Engineers. And he has issued some major reports on earthquake mitigation for a federal earthquake insurance program. And he was kind enough to tell us that maybe that program, this program does not exist yet. It's somewhat contemplated. So he belongs to many professional organizations, and I think we have to acknowledge his work. He was chair of the ASC Council on Disaster Risk Management. I think he has received awards for this particular work he's done, and especially work from the Technical Council on Lifeline Engineering, also known as TICLI. In October 2008, in the aftermath of the Wenchuan earthquake, which struck China, he went to Tongji University, participated to workshop on reconstruction alternatives for China. He went back again to China to give lectures at the International Symposium on Reliability Engineering and Risk Management. And so when I heard about that, I said, Craig, you can't speak in China without speaking to us. So he agreed to give us a talk somewhat similar to what he gave in China. So let us welcome Greg Taylor. Craig?
How do we do that? Okay. Well, thank you much, JP. I appreciate it. It just happens in China. If you get gray hair, people appreciate you. I mean, regardless of what you've actually done. So I wasn't unhappy about giving this lecture here because this is actually different. I didn't even think of this until a couple of years ago, and the reason it started was a question asked by Professor Trefunic many years ago at a, let's see, how do I go up and down? Oh, here it is. This one. Okay. So the outline, let's see if I've given it. Yeah. Okay. The outline is, first of all, I'm going to define robust simulation. Secondly, challenges in selecting a preferred and alternative catastrophe risk models, challenges to robust simulation itself, lessons from China, and then a summary. But the question that was raised, and it was actually by Professor Trefunic back in 2000, and he may not have phrased it this way, but I gave a presentation on how to define uncertainties given models uncertainties that you run through a big simulation program. And I would, if I had to redo it, I'd give a slightly different presentation, but it would be somewhat similar. And then he asked at the end of it, you have to watch out for questions from Professor Trefunic. How do I account for what I call exogenous, it's this fancy term, alternative view models and views. And this has become a really prominent issue in earthquake and hurricane and other areas. Is that the question you asked 10 years ago?
I don't remember. I might ask you something else.
For primitive mind, could you clearly define the terms endogenous and exogenous?
Oh, endogenous just means that when you model all these things, let me see if I've got when you model these, when you do a catastrophe risk model, which includes just a lot of submodels, like exposure and hazard or peril, vulnerability, systems, macroeconomic, then you look at alternatives, so you can find out the best alternatives. You have a decision criteria and all of this. In these, you have submodels as well, and you can have an uncertainty. So when you're modeling earthquakes, one of the big uncertainties is focal depth. So you can have a model of focal depths. We have a very bad model of focal depths in California right now, but and so you can model that. So that would be an endogenous uncertainty that you put into your modeling system, and you can model attenuation, and you might have a standard deviation of 0.55 or something like that in ln space, and you just model it and you run it through the whole model. You run each time you come up with a new value. So those are endogenous uncertainties. Exogenous uncertainties are those things that you don't put into your model, your preferred model. So most of our efforts, and they should be, are designed to find the models I prefer. You know, I like these better for this reason or that reason, you know, and
it comes from Greek. Gonis, goner, gonu is like parent, you derive from, and exhaust is outside. So something outside of what you have assumed.
yes.
Like literally translated.
Yeah, thank you. It is, yeah, you're right. And it also, the same terms are used in macroeconomics, so I had to test with that with Professor Rose. So robust simulation employs simulation procedures. We're only talking about simulation. I'm not here venturing into testing, which is a different story, to develop loss and gain distributions for a preferred model, that's the one I like, or you like, and a coherent competitive models for the range of outcomes. And this range is developed to indicate uncertainties in what is currently known. This is a completely different view of uncertainty analysis, and I'll tell you why it arose in just a second. So this kind of practice, I have a close friend, John Collins, who got an engineering mechanics PhD from UCLA, but he's now 75. He runs a big company of 60 people, largely PhDs. And they do missile risk analysis on all kinds of fancy things. And they do that, something like that, in their procedures. We had a presentation from Robert Lempert of RAND on how he did 100-year policy analysis, and he did the same thing. They used robust ensembles, is his expression, to get uncertain. Can you imagine figuring out what's going to happen in 100 years, you know? So climate change, climate conditioning, alternative insurance, reinsurance models for catastrophe. And so, and I have Rick Murnane, I mentioned in the first slide. He does a lot of work with MIT and Florida State and so on a lot of these issues. So he's going to give a presentation in Zurich next year on the same topic for hurricanes. In California, we don't know hurricanes very well. Okay. So here's the kind of model you're constantly seeing in terms of climate change, hurricanes, and so on. The results of the models are not precise outcomes. The results are a combination of outcomes from different modelers. And that's what is often presented as a result. This is from Kerry Emanuel of MIT. We could go over what it is, but you see the same thing on all kinds of diagrams in climate change. And what this does is it starts to reorient our view of how one should think about what one is doing. Instead of having a monopolistic view of what one is doing, which is a good thing to have, by the way, it's a good thing to want to be the best, you should have a competitive view that while you're doing something here at USC, somebody else at Stanford is doing something else, maybe along the same lines, and somebody at Texas is doing something else, And it's good to have this kind of competition in science. That's a good thing. So you have a competitive model as well as a monopolistic model of science and engineering. And you have to have the wherewithal or resources to handle this model. So we're talking about really important areas. Earthquake tends to be one of those areas when there are national building codes and so on involved. So it's a very different view of science. So these are the sub-models you have. Exposure, they all cause problems. Peril sources, peril propagation, path and distribution, facility vulnerabilities or fragilities, system vulnerabilities, macroeconomic outputs, decision procedures, stakeholder results. Each of these causes problems. You know, you can have specialists on some subtopic for peril sources, and so on. So, and as things have developed over the past 40 years, more and more the number of participants in this process has increased immensely. Oh, here's what happens. Some people are trying to shake up earthquake theory, and sometimes these things happen too fast. If one is thinking in terms of practice, one doesn't want to make changes too quickly without a lot of review. The recent USGS golden models, which will enter into the building codes, if they haven't done so already, did not have a lot of time to review all the submodels and so on. It's very important to have a lot of quality assurance time on these models. So what is true about these models and what makes it fit something like robust simulation is there's no unique solution for defining rates of occurrence of earthquakes. There are lots of ways one can do it. One can do this or that or this or that. I mean, you can come up with a lot of different solutions on it. Moment balancing, I used to really like this, but the more I think about it, moment balancing means that you've kind of got an energy budget. I think Professor Trefunic was using this back in 1985, something like it. But I used to like it because then people couldn't just throw in a big earthquake or increase the magnitude, maximum magnitude of an earthquake without having it impact the whole system, the regional system. But moment balancing is, you've got to figure out, you've got three different theories of time involved in earthquake. You've got clustering, which is being studied a lot now, where one earthquake causes another nearby. You have a cyclic behavior. Some people believe in what they call a characteristic earthquake theory, which is the earthquake occurs now and then its return interval is approximately 250 years. And then you have a much more random theory, which comes out of UCLA, that you just have the so-called Gutenberg-Richter law that dominates everything, so everything's kind of random with some association of faults. So these are not, these models have not been, are going to be discussed for a long time. I mean, one's not going to win. One's not going to win easily. So one should randomly assign specific months or years to events. Time is extremely important in asset management, as Professor Bardet is talking about, extremely important in finance and decision-making generally. And modeling years or months also facilitates multi-peril as well as cluster models. That means that if you've got a hurricane that hits Haiti and an earthquake occurs not long afterwards, you have to look at how the damage from the hurricane impacts potential damage from the earthquake and vice versa. So if you have things put into time units, you can say this occurred in month 1 and this occurred in month 3, and you look at the response. In Haiti there won't be any response, of course, but you know, you have to look at the response and see what happens and see the impact of one event on another. Or you can look at one big earthquake hitting and another hitting nearby, and so you model, it's called the Markov kind of modeling. So planar models have replaced the use of epicenters and hypocenters in US national models. That happened in the 1970s. 1960s, a lot of the models were epicenter models or hypocenter models. Synthetic models, which Professor Trefunic has done for as long as he's been working in this area, go beyond this in defining such details as asperities and barriers. They can incorporate a little bit of the dynamics of earthquake sources. Dynamics involve what happens are there permanent barriers or not permanent barriers, and if the rupture velocity goes through permanent barriers, does it go straight, follow the old mature fault, or does it go a little bit to 30 degrees or whatever? And this comes from Maria. There's no unique solution in defining the best synthetic model, and we'll see that in just a second. So what we have is a situation where we don't have unique models. We have different models. You have to have, as I say, resources to model these. Here's another problem that occurs that's very instructive about the great shakeout movement and all of that. This is Robert Graves, who actually did the shakeout modeling previously, and one could see how the waves propagated through the Earth. But look at downtown LA for 3 different velocity time histories. So here's one where the rupture comes from the center, so the rupture goes like that out, and here's another where the rupture comes from the north, and here's one where it comes from the south. And look at the differences that you can get just from doing the source differently in terms of rupture direction. This is just an enormous difference. Now, which one did they use in shakeout? Can anyone guess? You should know this. The structural engineers don't always like the results that come out.
Always pick the biggest.
Yes, thank you. Very good. Okay, got it. Okay. So next generation models have been developed by seasoned investigators given one database. There's a big database of maybe 3,500 records. But the probability given this database, all this evidence, did not yield a unique result. Now this is fascinating in terms of statistical theory and probability theory. This is not supposed to happen. Von Mises thought that the more data you got, the more you'd get an exact answer at the end. And your Bayesians sometimes claim when you have different investigators, eventually everything will converge. But it's not converging for these modelers because some are more interested in directivity and some have a different model of soils, and some want to emphasize how many data points from each earthquake you present, how to weight these differently, and so on and so forth. So you have all these different modelers with different interests and different goals, and they're not coming up with the same answers. And it's especially bad in the Midwest. And also mixing models. This is something I have a paper I wrote the paper this 18 months ago, but the reviewer of this paper was ill, and he just didn't, there wasn't oversight. But mathematically, there's an old distinction that's been very popular in the earthquake area called epistemic versus aleatory. And it's just totally incoherent. But you can show that mathematically. But I won't try to go into that. It was just a mathematical presentation. The more extensive database still has not revealed the scatter and high frequency motions. There might be not even the worst case, but the Parkfield event has a lot of high frequency motions. And Professor Trepunic can talk back now. He has, in his 1997 attenuation model, he has a very high standard deviation for high frequency motions. And the current NGA models are much lower, extremely lower. And it turns out this is probably very critical for codes, especially low-rise buildings on rock. I mean, that's where it seems to make a huge difference. Anybody who gets a chance should start looking at Professor Rosakis at Caltech. He's got some things on the web, so you can watch his lab experiments on rupture propagation for the earthquake model. So many alternative seismicity models. I mentioned the time-dependent models. These don't make as much difference as I thought. So I'm just saying 2.4% higher than the Kagan. And so these are UCLA folks who always emphasize more randomness. And I think cluster models could make a bigger difference, but I haven't studied them here. Changes in attenuation functions, though, over time have made a huge difference, especially in high-frequency motions. So that the losses are reduced 50% in some cases the codes, this has been a big issue on the codes. Greg, have you seen this issue come up? How the codes have changed a lot, near faults, based on bedrock motions? So extreme divergence in some cases. So it's a major issue. So do you want to express your opinion on this? Do you? Okay. Okay. So validation also is thoroughly required. Lost data are often proprietary, crude, uncertainties in strong ground motions and permanent ground deformations need to be accounted for, and so on. Validation procedures may be statistical. Still, some models may have almost no probability of being competitive. What that means is we studied one model that came out in some famous federally funded program, and it was a bridge structure model, and it had less than a 10 to the minus 9th chance of being true, valid. So you can rule out some models like that if you study them. And also you have a situation like this. You have a potential enormous contrast in whether or not your loss models contain engineering or don't, whether you go out and make site visits or contain engineering. So this would represent a potential value added if all of your buildings were built as you stated them and there wasn't any uncertainty. And so the investigation can possibly reduce your loss estimates enormously, and that of course can reduce things like premiums and so on a lot, and it can reduce reinsurance costs all the way downstream.
Greg,
how did
you get to this curve?
Oh, this curve is where you change. This curve comes from URS, but it's basically what you do is you change the uncertainty on your models depending upon how much engineering has gone into your models and the added information. So you know, some of the structural people can talk about this, but you have different levels. You have an empirical model, or just you categorize buildings by frame and a few other things, and height and so on. That's one level, the very lowest level. Another level would be a site inspection. Another level would be a very simple analytic 1 degree of freedom model, so on. You can go down, and the better you get, allegedly, the less uncertainty you have in how your buildings are going to perform. Okay. So robust modeling yields these fuzzy outcomes from precise calculations. You don't have to have fuzzy set theory to do this. You could use fuzzy set theory as one of your alternatives. And in addition, we know from well over 30 years of experience with the markets, stock markets and so on, and longer than that, that there are decision theories do not always require that you have a precise number. They can allow you to have a range of numbers. You can make decisions without having a precise number in your resulting analysis. And with the Fong Lu was at my presentation, and we just finished a paper on that in end of 2009 on very complex decision theory, but there are much simpler ones that still you can have the so-called mean variance and Black-Scholes and all of the offshoots of mean variance have all had two criteria, the mean return on investment and the standard deviation or variance on investment. Now, there's one big problem with what I've said so far. I'm assuming the law of large numbers, or probably the strong law of large numbers, in a lot of these discussions. I'm assuming that as you get enough simulations, what happens is, this is where the predicament arises. The confidence intervals decrease by a function of roughly 1 over the square root of n. So if you want to decrease your confidence intervals by a factor of 2, you increase the number of simulations by 4. And that's a rough rule. It actually works pretty well in Bootstrap. It works in classical theory. So what happens as you go along and you have 500,000 simulations, you have confidence intervals for any estimate virtually that are virtually close to the actual estimate. So that's where the paradox starts. That's where we need some other theory of confidence intervals, because the simulation process is purely formal, and what I'm coming up with here is not a purely formal assessment of what you actually know, confidence on what you actually know. It's actually a issue-related one. So, but in addition, you have there are cases where this doesn't work, where the 1 over square root of n rule doesn't work, and those are cases where you have wobble in your outcomes. You go along and all of a sudden boom, and then you go along and you get boom like this. This often happens in electrical engineering. Our incoming president has written papers on this topic because they deal with web demand and things like this. But there are many, so you have what's called really heavy tails in catastrophe modeling, and a lot of people have been writing on this. And that means that it's almost an all or nothing situation. You either get hit or don't get hit. It's not quite that, because we know we have smaller earthquakes and larger earthquakes and all of this stuff, but it's all, you don't get hit very often, but when you get hit hard. So to study these, there have been all of these tests proposed by different people, and I've studied these tests, but I've come up with my own hypothesis, which is you use what's called a Pareto distribution, which is a heavy tail distribution, severe distribution. It's been used for 100 years in the insurance industry. It's very simple. It's y equal x to the minus 1 plus whatever alpha, let's call it, And it turns out, so I just use it at the 90th centile, and I'm not trying to fit the actual findings. I'm not doing a fitting, I'm just doing a diagnostic, and I compare that to the 99th centile of the simulated distribution, and I have to use a little 99th centile. I can't just use the max, because the max just vanishes in this test, so I use 99th centile. And so the general rule is if alpha is less than or equal to 2, you don't have you have an infinite variance. You don't have a standard deviation. So the strong law of large numbers doesn't hold any longer. And if alpha is less than or equal to 1, then even the mean doesn't hold. And there's a famous distribution called the Cauchy and some others. The Cauchy distribution, it looks like the only thing that's stable maybe is the median. So you've got these strange things, and people have been studying them. I've got this wonderful book by a French guy named Sornet on what they're trying to do and how they're trying to use these in physics to explain all kinds of physical processes. And he tries to explain failures in the stock market by this. It's kind of a joke, but he's using something very similar to this. This is called the Pareto distribution. And you can use the Pareto distribution in a very simple way to assess whether you've got this problem. Now, I don't go any further. Yes?
Could you just say in a couple of sentences the physical assumptions that lead to these distributions? For example, the square root of n is basically a Brownian motion mode. What are the basic physical assumptions leading to Pareto? All these distributions have some physical.
Well, no, there's not. There's
equation which leads to.
Well, if you read Sornet, there's not one. There's a whole bunch of physical assumptions. But I'll just explain what I was trying to talk to some people today about. For earthquakes, what you have is something like stationary crustal properties, pretty much, with some fluctuations. That's the more what somebody like Sornet talks about in terms of the physical assumptions. You have a lot of different kinds of processes, but you have a lot of processes on a daily basis that are like this. They are extreme. Cracks form, somebody hurts his hips, You have a lot of processes where things just break down that we're just accustomed to. Your automobile tire goes flat. All kinds of processes are like this. It's just that hurricanes and earthquakes have so much more severity attached with them often, sometimes. So I can't explain, because there's not one type of physical phenomenon here. And somebody like Sornet's trying to use the power laws to explain a wide variety of things, and that he doesn't have a full answer for this. Does that help at all? I mean, but basically for earthquakes, you have something fairly stationary, which is the mantle, the lithosphere, and and the crust in the crust. But you have these periodic explosions, so to speak. So very rare. So it's going to differ quite a bit by the type of process. That's, I don't know. So what our next president talks about, he talks about Levy distributions, and part of that is alpha stable distributions and so on. But one should not automatically assume that earthquake loss distributions are unstable in this way, or alpha stable. You don't have to resort to extreme problems here. We did one portfolio which included a few Washington properties, Oregon properties, and California properties, and it started to look bad. It started to have fluctuations at about 50,000 samples that didn't belong with the 1 over square root of n rule. But we found out, we used this Pareto, this diagnostic, to start looking at not just the loss distribution, but also the distribution on values. And we found 3 values that were very high, so when those values got hit by some earthquake, you'd have this kind of motion. And when they weren't hit, you wouldn't have that, and it was throwing things off. We found out after you did 500,000, the loss distribution had an alpha of 5.3, which is pretty safe relative to earthquakes. Nothing close to 2, but the exposure value was 2.1 because you had these 3 properties which had so much higher value than the rest of the properties. Now let me explain that for many, many years, actuaries have been using alpha values below 2, sometimes as low as 0.5 in calculating reinsurance values. I've said this sometime before, but that means that they've way exaggerated the amount of reinsurance costs for a long time. But this kind of test starts to get at what the actual values might look like. The actual topography of this 99th centile, this tail, I think has lots of kinks and so on. There are lots of limits, like when a building collapses, like a pancake concrete building, that's a limit on the building. And there are lots of limits in nature too. There's a limit on maximum magnitude, whatever that may be. And one starts to take into account all these limits, and in insurance you have deductibles and all these different layers and so on. You have a maximum surplus, and you have too many. The topography of this is not a simple a priori thing like a Pareto distribution. Very often academics just deal with a priori distributions because that's all they have. They don't have data. But that's a dangerous thing to do. Like,
point number 3, you say if there's a calculable upper bound on losses and the variance is finite. If we had, the massive meteor hit the Earth and wipe out all life, that's the calculable upper bound, right? I mean, we've lost everything.
Yeah.
So, is it ever? When do you really?
Well, no, I have problems with this. With tsunamis, for instance, I have problems with the maximum tsunami risk. I do have problems that you're talking about, exactly. So, I mean, when do you ever reach this, Yeah. I mean, there's...
Or do we ever have, infinite variance? I mean, you wouldn't ever really have truly infinite variance on anything because you can't lose more than the entire value of the whole world.
Well,
It's got to be some finite number.
Yeah, you just may not be able to calculate it. You'd probably have to, instead of using forward simulations, you'd have to use reverse. You'd have to, no, to get that, very often you're going to have to use reverse simulations. I was reviewing a paper that had a similar issue, and they maybe had a 10,000-year return interval for failure of this building, but they were just using forward simulations and they weren't getting it. So they didn't see that you actually had an upper value, and when you don't see it, it
looks like you have infinite variance.
Yeah, it looks like it, and it looks like your structurally engineered project is always better, even under those circumstances, than an inferior design, when in fact, when you hit that 10,000-year limit, the other design is better because you've spent more money. You know, I'm just saying somebody didn't notice it because sometimes you have to use reverse modeling to get there. So right, thank you. Okay, so you seek the most divergent competitive models. This is what I've been suggesting to USGS. They've been trying to mix and match models, and sometimes it's like mixing oil and water. They just don't mix. They have different motivations. They have different parameters. They have different databases. Place the burden on those with alternative models. Deal with how to communicate risks in terms of ranges of outcomes. Rethink the idealizations. So when this starts to fail, you really have to start rethinking what you do with axioms and things, areas like, you have to be careful of emphasizing mathematics at the expense of reality. And the law of total probability has a hard time applying to this because you're talking about opinions. Opinions are often influenced by the group, and you don't ever know that you've got all the opinions. The NGA modelers do not have all the important opinions on the attenuation functions, and there may be some really bright kid out there somewhere who's got a better model. There's 7 billion people, and I figured out that if you divide by 10 to the 4th or 10 to the 5th, you've got a lot of really smart people. So my point is that it's very hard to claim that you can divide the world into these nice partitions of opinions, which are all overlapping. So lessons from China. So one lesson I learned from China was, as people here may know, there are some models that require days and days. These would be submodels on individual structures, geotechnical sites, or things like that. So the supercomputers might be running for 6 or 7 days. So you have to simplify these. And the way to think about simplifications is to think about them in terms of developing systems and emphasizing mechanisms for those that are really hard. But you also can pre-process a lot today. And I think the terms endogenous and exogenous are as ugly as aleatory and epistemic. So I think a better way to think about this is you have purely formal or mathematical ways of developing confidence intervals, and this is more of a substantive. It's also substantive model. You're actually looking at alternatives to your view, and it's more substantive. And I think my view is this is a much more mature model of what we actually know. It gives you a range of what we actually know, in spite of the fact you may still prefer your own model. So it's practiced in many disciplines that are very active and important. CAT diagnostics help to define dangerous distributions, which is why this whole problem arises. The 1/square root of n rule you're not getting anything out of that rule. Arbitrary weighting procedures may yield undesirable, unintended consequences. That's what's true of the epistemic aleatory stuff. You get multimodalism when you assume unimodalism and all this stuff, worse stuff than that. Robust simulation defines uncertainties as best we know them at a given time. So I want to thank everybody for just paying attention. I hope it made some sense. Any questions?
We're going to try something new here. Make sure that your questions are recorded. So any questions to Craig? Don't be intimidated by the microphone. It's just nothing really to be scared of. Anybody has a question for Craig?
Okay, Craig, I have a question.
But you have to speak in the microphone, Michel.
Okay. The problem is a formidably difficult one, I accept that, but can you think of a case, and just, not earthquakes, it's anything, financial markets, wars, whatever, where you have maybe a sequence of catastrophic events and enough data that you can come up with a model and then verify the model? The basic fundamental principle in science is to verify
formalism against data, against physics of the real world. Do we have an example like this? Something was predicted, or something could be post facto predicted as if though we didn't know the outcomes, and then we compare that with the outcomes so that you can test some of these ideas.
Test robust simulation like this?
Yes.
Oh, there's all kinds of cases like testing. Testing goes on all the time. I'm assuming you can do lots of testing.
No, but I mean, have you done any, or can you suggest a test, or can you illustrate a test for us? That's what I'm getting at.
We tested this bridge structure.
Sorry.
Yeah, I'm just
I
trying to
think
give you this example.
we are missing something here.
Okay.
We're missing your answer.
Okay, the bridge structure case, we actually had to run an enormous number of simulations given the models to see if the number of collapses as predicted could be verified or invalidated. The case was, okay, there were about 43 bridge structures that were estimated to collapse, and in the database, the actual database we had, there were 9 in Northridge. Okay, no, I'm not sure what but that was the exposure we dealt with. So we had to figure out, what we did was we actually figured out a way to come closer to 9 by changing the parameters. It was a fairly simple model, but we had to run loads of uncertain distributions on the Northridge earthquake through the bridge structures just to test. We didn't just test based on MMI or some best estimate. We tested based on a whole uncertainty evaluation. Yeah, that's one test.
Northridge earthquake, but for example, I don't know if it's called overpass or when you go on 5, there is an exit with a huge arch and circular thing that goes to 14. That thing has collapsed in 1971 and almost exactly the same way in 1994. So if you were to use that as a model and analyze the design criteria, everything that goes into the model, and see if you can predict 71, and then what was done afterwards, could you have predicted 1994? I'm looking at a recurrence of catastrophic events on a model that is more or less well defined.
Well, I think that from a structural engineering standpoint, I mean, this tends to be fairly easy. I mean, because you have all kinds of concrete buildings throughout the world that just failed in, fairly moderate earthquakes. I mean, it's not really hard to have some predictions like that at some level for some categories of buildings. I don't think that's terribly hard. I mean, something like Haiti is probably predictable if you have the earthquake model. So I don't think part of what you're saying is not hard. It's not the question. The question is really, can you estimate that precisely in your validation process? What you have is not just one earthquake, you have other earthquakes and so on. So you have to spread it around, and there isn't a lot of data outside of the Balkan region, and maybe China, maybe Tangshan, to do that kind of stuff. So yeah, the answer is you can definitely have lots of tests, and you can have experimental tests as well. I think those are fine. But there are certain marginal cases you're not going to test for very well. I think everybody agrees on that. You have to. Is that what you're asking? I'm saying that the case I'm talking about for Northridge, I didn't come up with an exact answer. Because I don't think there is one. But I came up with an answer which was good enough to be within the 30th to 50th centile range. I'm not getting what you're asking. Can I?
I'm asking, can you come up with, in any field, a case where the actual sequence of events can be used to verify the validity of the predicting model? The model predicts a catastrophic occurrence, or it doesn't. And there's a lot of things that goes into that model. Right, and you cannot be right all the time, but can you be right sufficient number of times in a particular instant, a particular physical environment that you consider that as an adequate actual verification of the approach?
Sure.
What you do in any case of, I regard validation processes as improvement processes as well. That's what I was trying to explain. So validation processes aren't simply stating what you did before. you can have your model, and it can give you your fuzzy outcomes. And that validation process, if it happens, you're going to change some of those fuzzy outcomes. That's what you're going to do with it. And you're not going to just sit still. It's not an eternal model. It's a model of what is best known at the time. So it's not supposed to be eternal. And in some cases, it's going to be so obvious, it's not even going to be, not going to be funny. Structural engineers look at some buildings and they're going to say, this will collapse in a 5.1 or something nearby, or with a 0.1 G for a few seconds, So those cases aren't going to be hard, but...
Okay, let me be specific.
Okay.
In 1987, we published a report on microzonation of Los Angeles Basin. And we published it and never touched it afterwards. And from 1987 to 1994, there was a whole sequence of earthquakes. And the report says at this location, this latitude and longitude, the probability that any future event will exceed that level of shaking is so much. And to our satisfaction, none of them have contradicted the model. And I would say this is maybe a beginning of validation, because we need hundreds of years to validate. But there is a theory, models, calculations that went into the formulation of the outcome, engineering outcome, something that engineers can use in the work. How good is it, right? And so there is a sequence of events afterwards, and then based on that sequence of outcomes, you can say, it was pretty good, right? But we didn't do any post-validation. We didn't do any post-modification. It was just published in 87 and wasn't touched.
No, I'm not saying you were lucky. I mean,
Oh, I'm sure we were lucky.
I'm not saying you were lucky, but no, I mean, the answer is, right now, back in Golden, Colorado, there are talks on how the NGA process has underestimated the actual database, let alone the post-validation isn't working well for some people, let alone a validation of a future earthquake. So, I mean, we have so many problems here. You're just raising another set for me. I mean, it's just, so I think I think partially you were just lucky. I mean, there's still so many questions. If you can tell me about how to deal with high frequency motions and the uncertainty, and I know, but I mean, that's one kind of issue, but that's going to be part of your outcome, right? And the longer period motions, have you solved that yet? I mean, so on. So,
We should try to get some questions from the audience now. Sorry, Michel.
I'm not part of the audience, right?
You're part of the audience, the rest of the audience, should I say.
I get the message.
Would you, any questions for our speaker? Well, if not, since I'm the microphone, I'm going to take one. I'm going to ask one. Now, have you been involved in the shakeout exercise? Here we have a major simulation efforts. We have simulated, I think about 2 years ago, I believe, right? A rupture on the southern part of the St. Andreas Fault. And then we have looked at all the consequences of this rupture. There's been a lot of simulations from the faults, from the propagation of the waves from the faults, and to the impact to various infrastructures, gas, water. We look at the fires and so on. And some of us are concerned that it's been handled mainly by economists, not by engineers. So I'd like to have your input here on what went right and what went wrong in these simulations. Can we trust them? Do they give us the right picture on what we could expect from a major rupture on the St. Andreas Fault?
Well, I don't want, just my opinion. My opinion is the function of shakeout is to stimulate interest in earthquakes and support for, to some extent, structural design, but largely for studies in seismic hazards, and also to help in some emergency response management where you look at maximum outcomes. And there are some engineers I know who have helped on the project. And I've shown you what Robert Graves did with 3 different sites. Now the site, obviously we know probably which one they wanted to use for downtown LA. They want to show that high-rise structures could fail. But that's one of a, I'd have to ask Robert, but it might be one of 3,000 possibilities here. So the answer is this is a little bit more like fantasy than it is like what I would be doing. But it has all these valuable uses. And that's what I'm talking is, I don't like having a parametric model of the final result for earthquake losses. But if somebody uses one, it can be very useful. I mean, it can do all kinds of things. So that's what I'm talking about, a mature view views the shakeout as stimulating a lot of people, and a lot of these people, all but Rick down at the bottom, have engaged in it. And I don't have to because I've got people who work for me who do this sort of stuff. So the answer is I haven't done it. I have a guess what they did on bridges. I think Caltrans was involved. At first they had a lot of bridge failures and so on. But I think it's a useful thing, but we have to watch out for hype too. So it's useful. Okay.
Yeah, it's a very relevant question. Actually, Lucille Jones, which is one of the leaders of this shakeout, is visiting USC today. She was meeting with Dr. Sinolakis to include the effect of tsunamis. So we have some kind of include now the evacuations of the coastal areas, follow up tsunamis which may hit our coastal margin. So that's something which is debating now. And I think USC is going to get involved in the shakeout. If you don't know what the shakeout is, it's a major exercise led by, I believe, SCAC and USGS, and basically trying to simulate the effect of earthquakes to prepare populations before actually it happens. So we know what to do, how to respond in case of an emergency. And it involves quite a lot of people. Last year, it was said that more people contributed to this event than people voted in the state of California. Of course, what was not taught, what they didn't tell you, that a lot of students, the children were involved, and those ones usually do not vote because they don't have the age of voting. But okay, so anyway, any more questions? Yes.
You talked about how combining models can lead to problems with inconsistencies, bimodalism, things like that. But one of the most common ways to deal with catastrophe models that I know of is to look at 17 different groups who each have a separate model that they're thinking of, especially, say, in weather modeling. Where's the hurricane going to hit? Well, these people predict here, these people predict here, blah, blah, blah. And we look for some sort of combination of all these models to try to get an answer. So is there a right way? Is there a wrong way? What's the best way to deal with that type of situation?
Well, I mean, my view of statistics here is roughly that where you don't have unique solutions, you still have. I prefer to use maximum likelihood rather than least squares. For this reason, it's a give and take. It's actually more like a transaction. It's a much more complicated thing. So I prefer to do it this way rather than that way, and you get your best answer, and you can do that. But the problem with the NGAs was they're in log space. And people don't understand log space very well, and when you start combining two different medians in log space, they don't yield the kind of Pythagorean theorem of total uncertainty squared equals epistemic uncertainty squared plus aleatory uncertainty squared. They yield something else, and actually your total value may be less than the maximum value when your medians at a given point differ. So you have real severe contradictions going on. So you can see this in some of the discussions, but what you should do is allow each competitor to outline coherently his own view, totally, all the way across the board. And that way, at least you have some coherence there. You're not mixing very, very different kinds of entities together. So that's and that's what's happening, I think, in climate change, and it's happening with hurricane forecasting, near-term forecasting. It's happening in all kinds of areas. So you're actually allowing more coherence. You're not bringing in all this incoherent stuff. That's all I'm saying. These are mathematical inconsistencies. There's serious reductio ad absurdum arguments against the NGA process, but that's okay. You know.
The question is whether coherency is something we should follow. Because, I mean, you have a room full of experts, and each one has a model, and if you average them out, you're actually throwing out one of the very good models.
Exactly. But yeah, no. The other criterion for science, this being really simple now, just for since you're, is fruitfulness. So you don't want to throw out fruitful models just to emphasize coherence. We're just teasing at this point.
I'd have an announcement. Maybe Fabian, you can make the announcement actually about the seminar tonight that EERI organized. Can you make it, or should I make it? There will be a seminar today, right, by Dr. Farzad Naim about NIS and e-defense. Dr. Farzad, as you know, Farzad Naim is the president of EERI and will be, is also, I think, the chair of a particular board, the external relation board at NIS. NIS stands for the Network for Earthquake Engineering Simulation. So there will be a presentation here, I believe, at 6:30 tonight. So you are invited to participate. Yes. The signs are posted on the doors, and I'm just doing now the verbal communication. So we look forward to seeing you here at 6:30 if you can make it. But before we close, I'd like to thank our speaker, Craig. Thank you, Craig. Okay, thank you. So this concludes the seminar. Thank you very much for your attendance.